Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to talk on the module Transferred Electron Devices from the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn in this module. First, the electron transfer and negative differential mobility in gun devices will be discussed. Second, velocity versus electric field curve for gun devices will be discussed in detail. Third, we will discuss about the different modes of operation of gun devices. So students, let us start with a basic introduction about the module. A transferred electron device is a moderate power device which has low oscillator phase noise, and it is a form of diode used at all microwave frequencies from 300 MHz to 300 GHz. These devices are also called as gun devices or gun diode. These devices are bulk devices and do not contain any junction as we see in all other microwave semiconductor devices. In some semiconductors, namely gallium arsenide, electron can exist in their normal low mass, high density, velocity state as well as in a high mass, low velocity state. And under the applications of steady electric field of sufficient strength, these electrons can be forced into high mass state. In this state, they forms domain or clusters which cross the field at some constant rate, causing the current to flow as a series of pulses. This is known as gun effect. So there is a special kind of diode which uses this effect consisting of epitaxial layer of N-type gallium arsenide grown on gallium arsenide substrate. So after the application of few volts of potential applied between the ohmic contacts to the substrate, and N layer produces the electric field which causes clusters. So current pulses so generated have some frequency, and this frequency of current pulses is determined by the transit time through this N layer and hence determined by thickness. So when the diode is mounted on a tuned cavity resonator, then current pulses causes oscillations generated by shock excitation and radio frequency RF power up to 1 watt at frequencies between 10 to 30 GHz can be obtained. So students, let us now discuss the historical background of the gun devices. The reason of alternative name of gun devices is transferred electron devices, which is due to the fact that for their operation, it depends on transfer of electrons between two different valleys in the conduction band of the semiconductor. So the experimental discovery was made by James Gunn in 1963. Clearly, already in this rudimentary form of a gun device, sinusoidal oscillations resulted. So Gunn was interested in what happened to the mobility of electrons in gallium arsenide. So at very high fields, and it does not arrive at a satisfactory explanation of his observations in the original paper, although the previously mentioned papers were already published. So instead, Kromer in 1964 explained the oscillations observed by Gunn by using the results from Hilsum 1962 and Ridley and Watkins in 1961. In following this explanation, we shall first discuss how electron transfer may lead to negative differential mobility NDM or equivalently negative differential resistivity NDR. Electron transfer and negative differential mobility. The detailed energy band diagram of gallium arsenide is shown in this figure, which is crucial to discuss the electron transfer effects. So students, as evident from this figure, the top of the valence band and the bottom of the conduction band both occurs at K equal to 0, indicating that gallium arsenide is a direct band gap semiconductor. The bottom of the conduction band, that is the lower valley, is of course where most electrons resides at room temperature. The conduction band has two other types of minima or valleys, however. One of these occurs in the 111 crystallographic direction at the Brillouin zone boundary, which is indicated by the dotted vertical line, and has an energy which is 0.32 electron volt, higher than the lower valley, and let us refer to this as the minimum as the upper valley. So the essence of the Gunn effect is that as electrons are accelerated by a high electric field, they may gain sufficient energy in order to be able to transfer to the upper valley. Let us assume that electrons reside in either of these two valleys, which are characterized by their usual parameters for that valley. So the effective mass of electrons is larger in the upper valley by a factor of about 8.2, while the mobility is smaller by an even larger ratio of about 53. Another important factor is the respective densities of states, which are proportional to the effective mass to 3 by 2 power. So the density of states in the upper valley must therefore be higher by about 23.5 times the number of valleys. Now let us study about the two-valley model in a more detailed way. In the two-valley model, we simply add the contributions to the current by the electrons in each valley with their respective concentrations and mobilities. That is, J vector is equal to E multiplied by N1 mu1 plus N2 mu2 multiplied by capital E vector. It is now easy to estimate the current density and the mobility. So now we introduce an average mobility for all the electrons, that is mu bar. So for very low and very high fields, J versus electric field graph is plotted in this figure. For intermediate fields, sigma is E N1 mu1 plus N2 mu2 equal to E N0 mu bar where mu bar is n1 mu1 plus n2 mu2 by n naught. Now sigma is this J will be equal to sigma E. It is equal to E n naught mu bar E vector, which is equal to minus E n naught V vector. So now if we guess the shape of the connecting part of the full curve, we arrive at the something which is the same as shown in this figure. If the transition from mu1 to mu2 occurs reasonably quickly, so there will be a portion of the curve with negative slope. That is the part where we shall focus on. Calculation of the velocity versus field curve. Electrons loses energy primarily by emitting the optical photons as they are accelerated through the crystal lattice. So the average time between the collisions which changes the momentum is the momentum relaxation time, which is of the order of 0.4 picosecond. This is derived from low field conductivity, while the average time between collisions in which the energy is lost, that is the energy relaxation time, is about 1 picosecond in gallium arsenide. So the effective time for transfer between valleys is estimated to be 1.5 picosecond as reported by Cromer in 1978. So most of the time it is actually expended for acceleration of the electron from the bottom of the band to epsilon minus epsilon 2 approximately 0.31 electron volt, while the actual interband transition is very fast once the electron has the required energy. Since there are frequent transitions between the two valleys, so in order to maintain the equilibrium, early theories of the gun effect assumed that the electrons in the two valleys, they are in thermal equilibrium at some higher temperature, the electron temperature, that is TE, corresponding to their increased energy. So we are also assuming that the type of statistical distribution function Maxwell-Boltzmann of the electrons is unchanged, something which may not be true for all cases. So the average thermal energy of the accelerated electrons can also be calculated, which is given by 3 by 2 kTe, where Kb is basically the Boltzmann constant, and the excess energy beyond the thermal energy at the ambient temperature, T must be supplied by the electric field on the average as fast as it is being lost by relaxation. So it is characterized by the energy relaxation time, that is tau E, and we can write E capital EV equal to 3 by 2 K TE minus T divided by tau E. Velocity versus field curves based on a unique electron temperature and the above simplified two-valley model can now be calculated. So in order to find TE, we approximate mu bar equal to N1 mu1 plus N2 mu2 by T N1 plus N2. So this is approximately equal to N1 mu1 divided by N1 plus N2. Since mu1 is very much greater than mu2. Now we also use N2 by N1 equal to R multiplied by exponential minus delta E divided by KTE, which is equal to density of states ratio multiplied by the Boltzmann factor. So now if we combine these two equations, then we get TE will be equal to capital T plus 2E tau E mu1 by 3 kb multiplied by E square multiplied by 1 plus R exponential minus delta E divided by KTE to the power minus 1, and V bar equal to mu1 E multiplied by 1 plus R exponential minus delta E by KTE to the power minus 1. So these equations thus enables us to estimate the electron temperature for electrons in gallium arsenide at a given electric field and lattice temperature. One feature to note over here is that the electron temperature initially increases with the square of the electric field in this model. So also note that we regard the temperature of the crystal lattice, that is capital T, as a constant. Now here we have just seen an example of the phenomena called as hot electrons, which is a concept to which we shall return in various other topics. So a better model uses one electron temperature for the lower valley and another one for the upper valley. The electrons in the upper valley tend to be close to the lattice temperature because the mobility is so low and because the electrons arriving from the lower valley have little kinetic energy left after transfer. Different modes of operation of gun devices. So students, let us first discuss the efficiency of a solid state device. The purpose of a typical solid state oscillator device is to convert the DC power to a microwave power. The efficiency will therefore be defined as the ratio of the output power, the microwave one, to the DC power supplied. So a hypothetical highly efficient gun device might be constructed such that it takes the maximum advantage of the negative differential mode NDM region by assuming that the electric field is uniform, although we know from the above discussion that this is impossible in practice. And by allowing the voltage to switch the current from the peak value to the minimum obtained for a higher electric field. That is, if the field is uniform, then the current voltage curve will have the same shape as the velocity field curve. This is shown in this figure where current and electric field waveforms in an ideal gun device with uniform electric field such that I by E curve follows the V by E curve. Alpha equal to IV by IP and beta is V naught by Vp. Now where V naught, Vp, Ip and IV were all the quantities marked in the figure which has been previously discussed. So the microwave power is obtained by finding the power for the fundamental gun device. Now let us discuss the Fourier component of the square waveforms for the voltage and the current, that is PAC equal to half multiplied by beta minus 1 multiplied by 1 minus alpha Vp Ip multiplied by 8 by pi square, and the DC power is Vp multiplied by beta multiplied by Ip plus IV by 2, and the efficiency then becomes eta equal to 1 minus alpha multiplied by beta minus 1 divided by 1 plus alpha multiplied by beta multiplied by 8 by pi square. So according to this expression, the maximum efficiency is obtained if the DC voltage is very high, that is large beta, and if the peak to valley ratio, that is 1 by alpha, in the current, that is velocity curve, is a maximum. So in gallium arsenide, alpha equal to 0.43 and the hypothetical maximum efficiency is 32%. Due to the fact that a uniform field distribution through the device is impossible and that the waveforms of voltage and current are non-ideal, practical efficiencies are much lower. So, the important feature of the expression of efficiency is that it predicts the efficiency as a function of the valley to peak velocity ratio alpha. This may be useful for a rough comparison of different materials for use in devices. Let us now discuss the dipole domain modes. Now that we have investigated the physics of transferred electron effect in gallium arsenide, let us now look at how the effect is being put to use in a device. So the device is typically packaged and inserted in a microwave resonant circuit whose schematic is shown in this figure. Now here the bias supply biases the device to the NDM region and is filtered with the inductances indicated, which prevents the microwave leakage. A bypass capacitor is used to couple the microwave resonant circuit represented by L, C and GL. So the resonant frequency of the microwave circuit without the gun device is Fr, and the corresponding period of oscillation is Tr equal to 1 by Fr. So the active device will oscillate at a frequency known as F oscillation, and the transit time of electrons across the full length of the device is tau t. There are three types of dipole domain modes which can typically occur. So over here we'll first discuss the transit time mode. In this mode, Tr equal to tau t, which is often also used in simple practical devices. Now here the voltage and the current waveforms are shown in this figure. So our domain starts at the cathode of the device. When the voltage increases above the critical or threshold voltage, so a roughly constant current flows while the domain travels through the device. So no major displacement current occurs in the contacts since the domain contains the equal amounts of positive and negative charge. Let us now discuss the second domain mode, that is the delayed domain mode. In this mode, 2 tau t is greater than Tr is greater than tau t. So the figure over here shows the voltage waveform, the moving domain charge, and the current waveform for this mode. Here, once the domain has been developed, a somewhat smaller voltage than Vt is sufficient to sustain the domain. The domain nucleates when the total circuit voltage passes the threshold voltage and then grows as it passes through the device. The domain decreases in size somewhat as the voltage again goes negative, but it is sustained until it reaches the anode. The device current is given by the velocity of the carriers outside the domain. This current decreases as the domain develops. After the domain has reached the anode, disappeared the average velocity, it will again increase and the current will go up. So the next domain nucleates when the voltage reaches Vt and the current stays high until this happens. So the current pulse therefore is somewhat broader than in case 1 above, which we discussed previously, resulting in higher efficiency which could reach 20%. Now here the frequency of oscillation becomes lower than 1 by tau t because of this delay. So the delayed domain mode requires more careful tuning of the device than the transit time mode. Let us now discuss the another domain mode, that is quenched domain limited space charge accumulation LSA mode. The waveforms for the quenched domain mode are shown in this figure, and the condition for the occurrence of this mode is that 2 tau t is greater than Tr is greater than tau s and F oscillation equal to 1 by tau t. Here tau s is the time which it takes for a domain to be quenched. The voltage must swing below Vs in order for the domain to be quenched. So the time tau s is roughly equal to the dielectric relaxation time with positive differential mobility, which we mentioned earlier. The devices can be made longer since the transit time condition no longer applies. If they are very long, more than one domain may tend to form, although this may be handled if all the domains can be quenched. So the condition for the full LSA mode domain never develops. It requires that first, the excess charge must not grow to a full domain in one period of the oscillation, and second is that the quenching time or the dielectric relaxation time must be less than the period. So students, let us now summarize what we have learnt in this module. First, the transferred electron devices or gun devices were discussed in terms of the electron transfer and negative differential mobility. Second, the velocity versus electric field curve for gun devices was discussed, where the expression of electron temperature was evaluated. Third, the different modes of operation of gun devices and in the domain transit mode. Their three types were discussed in detail. Thank you.